Hello, my name is Hao. I'm glad to share you our work in discriminate pointing attacks on unsupervised contrastive learning. This is a joint work with Kevin and Dina. Indiscriminate data poisoning is a technique to protect the data from being exploited by unauthorized users. In its setting, the dataset owner is an attacker who aims to perturb the data such that it do not lose its normal functionality but cannot be learned by any machine learning models. It means if somebody else, which we call victim, get those poison data and train a machine learning model on it, the model will have a better performance. During the past few years, many successful indiscriminate data poisoning methods have been developed. On CVR10, the accuracy can be attacked from 95% all the way down to 6%. However, all the prior works only consider attacking supervised learning and ignore the fact that there are so many unsupervised learning methods that the victim might use. This actually making all previous attacks vulnerable. For example, a simple way to break them is to use contrastive learning. Specifically, the victim can first learn representations by contrastive learning and then learn a classifier with the fixed representations. On CFR10, using any contrastive learning like Sinclair, Moco, BRIOL can bring the accuracy back to 80% from 6%. So in our work, we study the problem of how to poison contrastive learning. Our idea is to learn poisoning perturbation that can shortcut the contrastive learning. This means that the perturbation should provide the model with an easy way to minimize the contrastive learning loss without actually learning the real features. We hope that after being trained on the poison data, the model will align the poison views based on the poisoning perturbation. But the model cannot align clean views because it does not learn the real features. To realize our idea, we propose a solution called contrastive poisoning. At a high level, it co-learns the poisoning perturbation together with a neural network model to minimize the contrastive learning loss. We emphasize that there are two key technical points that are important to the effectiveness of the learned contrastive poisoning. Firstly, we need to backpropagate the gradient through the data augmentation. Data augmentation is crucial to the contrastive learning. Thus, we have to differentiate and train the poisoning perturbation to shortcut the augmentation operators. Secondly, we need to backpropagate through the momentum encoder. Momentum encoder is a common design to stabilize the training of contrastive learning algorithms. For example, both Moco and BYOL adopt this design. To allow the poisoning perturbation to shortcut the momentum encoder, it is essential to backpropagate the gradient from the momentum branch. In our experiments, we consider two variants of our method. Sample-wise poisoning, where each data point has its own perturbation, and class-wise poisoning, where data points from the same class share the same perturbation. The result shows that both sample-wise and class-wise poisoning are highly effective for different datasets and different algorithms. For example, on CIFAR10, our method significantly decreases accuracy from 90% to around 50%. Moreover, comparing the lowest attack accuracy, we observe that Moco and BYOL is less vulnerable than Sinclair. We attribute this enhanced robustness to the presence of the momentum encoder in Moco and BYOL. Because it is more challenging for the attacker to shortcut both the normal encoder and the momentum encoder. Our method also works when the attacker does not know the victim's algorithm. In the table, as highlighted by the blue color, class-wise contrastive poisoning can always decrease accuracy to around 6%, regardless of which algorithm the victim uses. This indicates a high transferability of our method. Further, we emphasize that our method not only attacks contrastive learning, but also being effective on attacking supervised learning. As the table shows, our class-wise poisoning can decrease the CIFAR10 accuracies to 10% for the supervised learning algorithms. This result is significant and suggests that the victim cannot define our attack even if he labels all the poison data and performs supervised learning. In summary, our work for the first time studied the problem of indiscriminate data poisoning on unsupervised contrastive learning. We also propose a highly effective solution called contrastive poisoning, which attacks both supervised and contrastive learning. Our code and paper is released. Please consider check it out. Thank you.